for this chapter. There are four sections together for chapter 8, which are about the multivariable calculus. Multivariable, that means the functions of several variables. So for this section 8.1, we're going to start with introduce you how what the function of the several variables and how to evaluate the value and what the graph looks like, something like that. Just give you a big picture of the functions that you're going to deal with for chapter 8. And then 8.2, we start to do the derivative of the functions of the several variables. And then 8.3, we're going to find local max, local min, similar to the technique or the concept that you did when you had to find the local max, local min for the graph in general, or remember like the maximum revenue, the minimum cost, something like that, use a function of one variable. But for this chapter, going to be more than one variable. And then the last section, the 8.4, gonna be the certain technique is called the Lagrange multiplier. That's another technique to find the absolute max, absolute min for the functions of several variable. Kind of upgrade from function of 1x into the function of the xy or the xyz. So make it into the bigger group of the function that we can deal with. All right, for 8.1, the functions of several variables. For this one, as we, the general notation, normally they don't use y equals f of x. They can use the z as a function of x and y. For this case, as you see the z on the left-hand side of the equal sign, the x and y as altogether as the expression on the right side, the z is called the dependent variable. X, y, they are independent variable. So when you think about the domain and range for y equals f of x, this case is a function of the one variable. Okay, the x here is called independent variable. And the y here is called independent. Oh, sorry, the other way around. So y is called dependent variable because y depends on the x, right? And similar concept, z on the left-hand side. So this one is dependent variable where both x and y, they are independent variable. So you're gonna get y depends on the x value and y value. So the domain gonna be the set of the value x and y, and the range gonna be the value of the z. And the graph in general, for z depends on both x and y. You're gonna have like the graph as a surface in 3-dimensional. Okay, no worry about that. So as you know, the point, the c value depends on the coordinate x and y. So you're gonna replace x and y into the expression and to come up with the value z. So let's go to the evaluation of the function of the multiple variables. So like same thing, wherever you see x, you replace in the x spot. You see y, you put in the y spot. For the first problem, the function fxy is x squared minus 7 times xy minus y squared. We're gonna find the first one. You see the format. The first coordinate is the x. The second coordinate is the y. So that means we're gonna replace x with the 0 and replace the y with the value 1. And that's all you have to do. And then simplify the numbers. We have 0 minus 1. So the number is 1. The second point, the second part, the x is 3, the y is negative 2. So gonna be 3 squared minus 7 times 3 times negative 2 minus, this is negative 2, minus negative 2 squared. And then clean up the numbers again. 3 squared, that's 9, minus negative 7 times 3 times negative 2, that becomes positive, right? Positive side. That is 42. So 9 plus 42, and then minus 4. And that should be, that's 50. What would that be? Gonna be 47, I believe. So 9 plus 42 minus 4.
Yeah, you're good. You're good.
That with 47, basically just like work on each term one at a time. And then the last one is the same way. This time x going to be negative root 5 and y is square root 5. X squared going to be negative square root 5 squared minus 7 times negative square root 5 times square root 5 for the y and then minus square root 5 squared. Square root 5 square with the negative side. When you square the negative side become positive. So the first term is 5. The next term, negative, negative becomes positive. 5, square root 5 and square root 5 becomes positive 5. 5 and 7 becomes 35. And then the last one is negative 5. So the answer that comes up to be 35. So just the same routine as when you evaluate the function. You just replace the right number in the right spot. Okay. And the function that we're going to use very often in the business application is the Cobb-Douglas production function. As a function depends on both x and y. We call it one represent the labor and the other one for the production, something like that. And then for the, let me see. Yeah, we're gonna see the Cobb-Douglas, the capital and the labor. Sorry, I was wrong. So one is for the labor and the other one for the production. So for at this point, we're gonna just know how to evaluate, or you should feel comfortable to evaluate the function value. So what we have, the x is 27, the y is 125, and you have done this, remember, like as part of the implicit differentiation like earlier. So to compute the f at 27, 125 as a normal routine, just plug it in. The x is 27 to the power 1/3 and the y is 125 to the power 2/3. And then simplify. The third root of 27, that is 3. And the third root of 25, and 125 is 5. So this can be 5 squared. So what we have is 10 times 3, that's 30, multiplied by 25. That come out to be 750.